All right, AP Chemistry. This is part 7 of the answers to the Christmas winter assignment. I had some technical difficulties for the last 24 hours or so, so I think I've gotten them resolved. So hopefully we'll be able to progress and get this done today. It's Friday, December the 27th right now. So the last video completed water, and I was working on NH3. So let's go ahead and do this. So we're going to draw a Lewis dot. All right, so we have 1 nitrogen times 5 valence electrons, 3 hydrogens times 1 times 1. Nitrogen goes in the middle, hydrogen never does. You draw it as symmetrically as possible, not knowing really what the geometry is, so pretty much like that. Not with angles, you don't want to go there, not when you're trying to figure out the Lewis dot. Okay, so we have 8 electrons to deal with here. So that does it. You have an octet around nitrogen. Hydrogen has its octet with 2 electrons each, and that's that. Okay, so electron domains, how many? It simply places where there are at least a pair of electrons. It could be 2 pairs, that's a double bond. It could be 3 pairs, that's a triple. But it has at least a pair of electrons. So you have 1 there at that hydrogen, 1 at that hydrogen, 1 at that hydrogen, and 1 at that hydrogen. So there's 4 electron domains. Okay, and write the AX notation. So there's 1, 2, 3 bonding domains, and there's 1 non-bonding domain. So the number of electron domains is simply always the sum total of the X and the E subscript. Whatever that adds up to, that's the electron domains. If you pull your VSEPR sheet open, anything with 4 electron domains, it doesn't matter whether it has, what the AX notation is. If it has 4 electron domains, it's sp3. Okay, so 4 electron domains means that it's tetrahedral domain geometry, one of these, and that it's AX3E1 means it's trigonal pyramidal shape. So it's tetra, domain geometry, 4 electron domains, and trigonal pyramidal. So again, that's basically a nitrogen up here. You have a hydrogen coming out directly to the side. You have 1 going backwards away from you. That's the dashed line. And then you have a big wedge one coming out. That's coming out towards you. So it's a pyramid, a 3-sided pyramid. 1, 2, and then the other side is over there on the back side there. Okay, trigonal pyramidal. All right, and that's everything it asked for. Okay, so the next one is C2H4. So again, draw it as symmetrically as you can. So there's 4 H's, so 2 will go here, and 2 will go here. And we have C. So you have 12 electrons to distribute. So we put 2 here. We go ahead and create single bonds everywhere. Single bonds are sigma bonds, and a couple single bonds there. So we have 2, 4, 6, 8, 10. We need to have 12, and carbon doesn't have an octet, so you put 2 more in there, and you have a double bond. So now there's 2 central atoms. They're both identical to each other. They're just mirror images of each other. But count the electron domains. So there's 1 between that hydrogen and the carbon, 1 between that hydrogen and the carbon, and 1 between the carbons. 2, even though it's a double bond, it's 1 electron domain. So electron domains equals 3. Okay. And 3 electron domains, come over here, is an sp2. Again, remember, it needs to create 3 bonds if it has 3 electron domains. So you started with an S and a px and a py, and you come out with sp2, sp2, sp2. You start with 3 orbitals, you end up with 3 orbitals. That's a py there. Okay, sp2, so you end up with the same number of orbitals that you started with. And then the pz is unhybridized. So it's available to form a double bond. It doesn't always, but it's available to do it. All right, so what else do they want to know? They want to know the domain geometry. So if it's 3, then you come up here. 3s are trigonal planar. And we didn't write the ax notation. Again, we're just dealing with one of the carbons here. So it's, I'll come over here, kind of getting all over the place here. Let me draw a line here. So it's AX3E0. We're just talking about this carbon, but everything we're saying for this carbon applies to this carbon over here. They're both central atoms. So anytime you have an E0, then that means the domain geometry and the molecular geometry, in other words, the actual shape, are the same. So this is also trig planar. Okay, and I think that's everything we need to write for that. So what it's going to form is a single sigma bond. That's a direct bond in between the two atoms. Just think about it logically. A bond would like to form directly between the two atoms that it's bonding. That's the natural place for it to be, is right in between. That's a sigma bond. Between this carbon and this hydrogen, sigma bond. Carbon, hydrogen, sigma bond, and between carbon, carbon, sigma bond. But there's not enough room for two bonds in between this, so the second bond, the double bond, is a pi bond, so it basically sticks up over the top and comes down around the bottom. That's the same pi bond that does that. Okay, so it's up here, it's down here. It can't be in between because there's just not enough space. So it's a very logical layout for these bonds. It's not really that tricky if you think about it. And if you happen to have a third bond, a triple bond, well, we'll see that in the next one. Okay, so that's it for CH4. All right, let's do HCN. So we have H is 1, C is 4, N is 5. So we're going to have 10 electrons there. So H can't be in the center. C is always in the center pretty much, almost always. Okay, so we have 10 electrons, so we have single bonds there. We form an octet around the outside atom, nitrogen. Hydrogen already has an octet. And so we have 8 and 2 is 10. So we've used all the electrons we need, but carbon doesn't have an octet. So we can't add or subtract any electrons. We have to just rearrange them. So we're going to take this pair here and this pair here, and we're going to stick them in between and make them a triple bond. Okay, so there you go. That's hydrogen cyanide. And so how many electron domains? Again, for the geometry, you're only concerned with the central atom there. And so it has one electron domain there, the triple bond, and one electron domain there, the single bond. And that's 2 electron domains. So if you come over here, 2 electron domains, there's only one possibility, and that's an sp, and it's linear. It's an AX2E0. There's no lone pairs there, so AX2E0. That means it's linear and linear. Linear domain geometry, linear molecular geometry. It actually is a straight line. It's sp. Again, that's going to be S and a px. That's how you break that down. And you're going to end up with 2 of those. If you start off with 2 orbitals, you end up with 2 orbitals. So S, px. Well, there it is. No, I've already finished that. Okay, so S, px. So there's 2 orbitals right there, and they form an sp orbital. Now you have 2 unhybridized p orbitals. That's the py and the pz. And this forms the double bond. And this forms the triple bond. So only an sp configuration can have a triple bond. It doesn't have to always have a triple bond. It doesn't even have to have a double bond. But it's the only one of the configurations that can have a triple bond. Okay, so where's that bond? Well, everything wants to be a sigma bond if it can, directly in between. So this single bond is directly between carbon and hydrogen. That's the logical place for a bond to be. And then there's a single bond between the carbon and nitrogen. That's the logical place for one of those bonds to be. But then the second bond can't fit in that same space. There's no space for those electrons in there. So they go up and above and down below. So that's the P. We'll say that that's the py unhybridized orbital that's forming this pi bond. Again, it's not called a p bond. It's called a pi bond. And then you have another one, and I'm terrible at perspective, so I'm not going to try it. It's coming straight out towards you, over and back, and then it goes back into the page and over and back out. So it's going around in this direction, and that's going to be the PZ. That'll form the triple bond. Again, you'd like to be in between the two naturally, so sigma bonds always are, but then a second and third bond have to be outside of that area because there's just not enough room to fit those electrons in there. Okay, so that's it. So you have two pi bonds for HCN. One forms a double bond, one forms a triple bond. Okay, let's keep going. All right, so you got all kinds of things going on here. So this is a little bit more complicated molecule than we usually do. So for each element in the chloric acid, give the following: the electron domains of the chlorine. So start off with the chlorine. And so the chlorine, how many electron domains does this chlorine have? It has 1, 2, 3, 4. So the domain geometry is going to be tetrahedral. Again, you're just going over here. Anything with 4 electron domains is going to be tetrahedral. Since they're all bonding, let's just go ahead and write the AX notation. It's AX4E0. There's no lone pairs. All 4 are bonding. Oh, excuse me, I lied. It's AX3E1. Looking at the wrong atom there. It's AX3E1. It is still tetra, though. Okay, but AX3E1, you come over here. There it is. It's trigonal pyramidal. You kind of have to use your imagination to see this in 3 dimensions. It's forming a 3-sided pyramid. Hybridization. Now, if it's got 4 electron domains, the hybridization is going to be sp3. Again, just come to this sheet. Anything with 4 electron domains is sp3. And the approximate bond angle. So normally a tetrahedral is going to have 109.5. So for a methane molecule, which has a carbon and 4 hydrogens. But this one's got a lone pair, so it's pushing. These 3 are not really going off to the side. They're going kind of, you could think of them as, it's a little hard to picture this in the geometry here. You think of this lone pair as being up on top of the carbon right here, then these are getting pushed down like a pyramid away from it. So anyway, what the lone pairs always do is they make the bond angle less than what it would be if there was a bonding atom right there. So all you can say about it is it's going to be less than 109.5. How much less? I don't know. 106, 107. And I'm off the screen. Sorry about that. I'm off the screen. Okay, there we go. So all we've been dealing with is this chlorine right here. So it's less than 109.5 because it's got a lone pair and then 3 bonding, sp3. Okay. All right. Let's go on to the next page. Okay, so I'm not going to do all of the oxygens here. We'll just do the one on the top. The one on the top is going to be identical to the one on the left. It won't be identical, however, to the one on the right. That's different. But let's just do this one and then we'll move on. So electron domains. It has 1, 2, 3. Okay. All right, so now we're going to do the oxygen on the top side here. It's exactly the same as the oxygen on the left, although it is different from the one on the right. But we're just going to do this one and then move on. So the first thing it's asking about it is electron domains. So there's 1, 2, 3. That oxygen has 3 electron domains. Therefore, its domain geometry, very simply, if it's got 3 electron domains, there's 3 right there and there, it's going to be trigonal planar. Okay, molecular geometry. So let's write the AX notation. It's A. It only has one bonding location. That's between the that oxygen and the chlorine, that one. So it's AX1, E2. Two different locations where it has non-bonding electrons. So we come over here. And we don't see that. And the reason we don't is this sheet is really designed for central atoms. But it's okay. It doesn't have to be. You just have to kind of understand the concept. So it has 3 electron domains right here. It's AX1E2. So its molecular geometry, it really doesn't have a molecular geometry. Its molecular geometry is dictated by the chlorine. That's the one that has the molecular geometry. That's the one that's determining the angle between this oxygen, and this oxygen. So it really doesn't have a molecular geometry, so you just say none, because it's an outside atom. But it does have hybridization. Since it has 3 electron domains, it has sp2, because it needs to bond. It needs to have a bond, an orbital in 3 different locations. Even the lone pairs need an orbital. So remember what that means. S, px, py. So that's sp2. You start with 3 orbitals, you end up with 3 orbitals. You end up with sp2, sp2, sp2. Those are all blended together. These 3 blended together, and they come out with 3 identical orbitals. Okay, so what does that mean? It means that this is an sp2 right here. It's a sigma bond between, it bonds with the carbon with an sp2. It holds these lone pair electrons with an sp2, and it holds these lone pair electrons with an sp2. It needs 3 different bonds to hold on to all 3 of its electron domains. Approximate bond angle, again, it's none. It's the chlorine, the central atom, that's dictating the bond angle. We've already talked about chlorine, so this one is none. All right. Let's keep moving on. Okay, so CH4, we've seen this one many times before. It's one of my favorite molecules because it kind of shows a lot of different things at the same time. So what's the domain geometry of C2H4? Hang on a sec. Okay, so this is the same as on the previous page. I actually meant to delete one of these, but I didn't, so let's do it again. It doesn't hurt, and we'll do it quickly. So what's the domain geometry of C2H4? Well, of the C, it's got 1, 2, 3 bonding electron domains. So that domain geometry is going to be trigonal planar. Getting this straight off the same sheet, so go have that sheet by your side. What's the molecular geometry? Okay, it's bonded in all 3 places, A, X, 3, E0. Again, we're only dealing with one of the carbons, but the other one is identical. So that's also going to be trigonal planar. As long as it's an E0, the names are going to be the same. What is the angle between bonds of C2H4? All right, so if it's trigonal planar, then they're going to be 120 degrees. And they're all bonded. There's no lone pairs to push the angle together. So you basically have a circle divided by 3, 360 degrees divided by 3. So that's going to be 120 degrees. Okay? So you know that a circle has 360, and if you divide that by 3, 1, 2, 3, each one of these is 120. All right, how many electron domains surround the carbon atom? 1, 2, 3. So we're beating this to death, but let's be sure we get this. What is the steric number of the carbon atom? It's 3. It's the same thing as the number of electron domains. It's just another name for it. What is the AX notation? We just gave that above. What is the hybridization of each carbon? We talked about that already. It's sp2. 3 electron domains is going to give you sp2. Again, go to your sheet and look at that. What is the hybridization of each hydrogen? Okay, hydrogen doesn't hybridize. It doesn't have a p orbital. You must have a p orbital to hybridize. The only thing it has is a 1s orbital. That's not a hybridization, but that's what it has. So it bonds with its 1s orbital. It's the only orbital it has. Identify how many sigma bonds in C2H4. So every single bond is a sigma bond. Okay, bonds would prefer to be sigma bonds. They prefer to be directly in between the two atoms they're bonding. So there's 1, there's 2, there's 3, there's 4, and there's 5. You can't have more than one sigma bond in between any two atoms. So there's, what did I say? 1, 2, 3, 4, 5. So there's 5. How many pi bonds? So the double bond is a pi bond. It doesn't really exist in between the carbons. It sticks down here. We talked about this, and it sticks up here. It has to go to the outside because there's no space in between the carbons for another bond. There's already a sigma bond there. So identify the pi bonds, and there it is. So there's one of there. There's one, and you can call it pi. So that's the pi, and this is the same pi, same bond. Okay, that's it. Let's move on. We're almost done. Okay, I'm going to give you one on molecular orbital theory here. All right, so this is the molecular orbital diagram. I seriously doubt they would ask you to draw one of these. You should recognize it, though, that for the periodic table, if we just talk about the second row, and I do not believe there's any way they would ever give you one of these beyond the second row, but we're talking about these elements up here. Of course, these also, form molecular orbitals down here, but mainly they're going to ask you about these. So with the first three in the p orbital, boron, carbon, and nitrogen, the pi is going to be down below this sigma. So these two are going to be switched. That's the only difference between, that's correct. The pi is going to be below this sigma here. That's the only difference between this one, which is for the last three elements, oxygen, fluorine, and neon. So for oxygen, fluorine, and neon, the sigma is down below the pi. So just put a light circle. That's the only ones that will be different between the first three and the last three. And for boron, carbon, and nitrogen, these two will be switched. Pi will be below sigma. Okay, other than that, let's go on and do this. So what you're doing is for oxygen, you're building an Aufbau. We're only dealing with the second orbital, so we're not interested in the 2 electrons of the first orbital. They're already sitting there. They have nothing to do with bonding. So what we look is how many valence electrons does oxygen have? And we know already it has 1, 2, 3, 4, 5, 6. So what we do is, here's oxygen atom number 1. And it has, first it fills this 2s, and then it fills the same 2s. Now it goes up to the 2p. And using Hund's rule, it fills up this first, this second, this third. So there's 1, 2, 3, 4, 5. We need one more, so we go back to the px, and we put the down arrow. Okay, and that's what the Aufbau looks like for an oxygen atom, for the second orbital of an oxygen atom. The other side's going to be exactly the same. I just like to draw it in order to emphasize the order so you get used to that concept. And there we go. Okay, so those are 2 oxygen atoms. Now, are they going to bond to form an oxygen molecule? So this is an O atom, and this is an O2 molecule in the middle. This represents putting them together. That's the molecule. These are the atoms, and this is the molecule and we're going to see if those two will join together to form a molecule. So it's a really easy process. You just take them one at a time, one from each side, and you just put them in order, in ascending order of the orbitals. So we start with this guy and we put him up. I'm going to check him off. And then we take this guy and we put him down. It reverses spin because they have to reverse spin if they're in the same orbital. We check him off. Okay, at this point, you'd have a bond. What does the downhill mean? It means these electrons are going to an lower energy level. That's good. That's what they want to do if they want to form a bond. They want to come together and be at a lower energy. That makes them more stable. Okay, but we're not done. So now we got to take this guy and put him up here. Again, you can just reverse the arrows as needed. The first one will be up, the second one will be down. Check him off. And now take this one, put him down, and check him off. So now we can see the 2s orbital doesn't have anything to do with bonding, because these are called bonding orbitals and these are called anti-bonding orbitals. Anything where it has to climb uphill to a higher energy level, it doesn't like to do that. That makes the molecule less stable and makes, in other words, the atoms don't want to come together and form a bond if they have to go to higher energy. It doesn't make sense. Nobody wants to go to higher energy. Things want to go down. You drop a pencil from your desk, it goes down, it doesn't go up. Things want to go to lower energy. So we have 2 at the lower energy, 2 at the higher energy. They basically cancel each other out. So the 2s orbital has nothing to do with the bonding here. So now we go up to the p orbital and we do the same thing. We're going to start with this electron right here. We're going to put it right here in this sigma 2p orbital. Now we're going to take this first electron on this side and we're going to put it down spin the same orbital. Now that orbital's filled, and now we keep going. This one goes here. This one goes here. Same as Hund's rule. Then this third one comes here and pairs up there, and this third one comes here and pairs up there. Now this fourth one right here, everything down here is full, so it comes up here. And now this fourth one, because of Hund's rule, doesn't go next to this one, it goes right there. All right, and there you go. You've filled it in. You've accounted for all 12 of the valence electrons, 6 from this oxygen, 6 from this oxygen. And now it's simply a matter of computing the bond order, and that tells you how many bonds you have. So we've drawn the configuration, compute the bond order. So the bond order is BO, bond order, equals bonding electrons minus anti-bonding electrons divided by 2. Okay, so let me go ahead and do that down here, that calculation. So how many bonding? It's the ones at the lower energy level for its particular orbital. So these two, there's 1, 2. These are anti-bonding. So 1, 2, then we go up here 3, 4, 5, 6, 7, 8. So those are all on downhill dashed lines. So that means there's 8 minus the anti-bonding. Those are the ones you have to go uphill to get to. So there's these 2 up here, so that's 1, 2. And then up on this side, there's these 2 only, 3, 4. 1, 2, 3, 4. And you divide that by 2, so 8 minus 4 divided by 2 equals 2. All right, so that's the bond order. That's what we're looking for. It's also the answer to this question. How many, if any, bonds does oxygen have? It has 2. So we know that oxygen has a double bond. Looks like that. So it has a double bond. Does hydrogen, I never changed that error. Does oxygen bond? Yes, has a double bond. All right, if we'd had a bond order of 0, there's no such thing as a negative bond order. You're always going to have more or the same number of bonding as anti-bonding. There's no such thing as a negative. But if it had been 0, there would have been no bond. Helium's an example of that. Okay, yes. Why? Because bond order, BO, is greater than 0. You can have fractional bond orders, by the way, but we haven't seen one, and just know that they can exist. Is greater than 0. Okay, is it O2 paramagnetic or diamagnetic? So the answer is, if you have unpaired electrons, it is paramagnetic. That means, just like that video we saw once upon a time, a water will stick in between a powerful magnet. It'll just suspend itself in between, within a powerful magnet. So it's basically a magnetic material. So paramagnetic. Why? Because, very simple explanation, it has unpaired electrons. These these two right here. Those are unpaired, okay, and so that would be. If you go 2 elements to the left, carbon, you would have stopped right here. It doesn't have any unpaired electrons. You would have stopped with those. You wouldn't have those two up there, and that would make carbon diamagnetic. Okay, well, that's the assignment, guys. It's probably about 6 hours worth of videos I haven't counted, plus another 6 hours on your own. I told you this are 4 to 6 hours. I told you this was going to be about a 10 to 12 hour assignment. It wasn't going to necessarily be a rollover assignment. So I hope you got through it. I hope you pace yourself. This does count as tests. It is due on Tuesday, January the 7th, at the end of the day. You need to get it done. It's just like any other test. You have to finish by the end of the testing period, and this is a test. It's not just an assignment that can float. So please pace yourself. Do it with someone else. Make it kind of fun. Get together with someone else in the class and work with someone, okay? Even introduce yourself to someone you don't know that well, if you know how to get in touch with them. Okay, so the deal is the tutoring is on the first page. And I think I left all those at school. So let's see if I can bring it up real quick. The tutoring schedule. There it is right there. So Thursday, January 2nd from 9 to 1 p.m. we're going to do kinetics. We started kinetics in the last week before the break. We didn't finish it. I really recommend you do these. This isn't just, if you're serious about challenging this test and really doing well, these are subjects we probably are not going to get to in the regular class session for the last 3 weeks. And it's actually 3 weeks minus 1 day. So we're really going to have to push things. So I'd recommend you come to these. If you come to them, please be on time, because if you miss the first half hour, you're going to be lost. And it won't, if there are people there, it's not fair that I have to start over for someone. So be there, I would say, at the absolute latest, 9:05 or 9:10. Okay, get there on time. That's why I make them start a little bit late, so you can get yourself out of bed and get there. On Friday, we're going to do nuclear and organic chemistry. Really, organic chemistry is just about knowing some names, nomenclature, and things like that. And then on Saturday, we're going to do a really important topic. It gets into things like oxidation numbers, redox reactions. It's not heavily tested, but it is definitely tested. Every AP I've seen has electrochemistry on it. It's basically the chemistry of batteries. How do chemicals produce electricity? And it's kind of an interesting subject. Okay, and that's going to be Saturday again. The times are all the same. If you need general tutoring, I can do it for maybe an hour or so after each of these sessions till about 2 o'clock. Or if nobody shows up, I'll do it then. But I hope to get a good turnout for these, because I really want you to be successful in the test. And it's going to take a special effort to do it. This is not just an ordinary class, and it's not just an ordinary test. So anyway, I hope you had a Merry Christmas, whatever you celebrate, and have a Happy New Year coming up. And if you need to pick up an assignment, just come by the classroom, or I'll keep your eye on this particular module, and I may post some instructions to get an assignment if you haven't picked one up already. Okay, so Happy New Year, and we'll see you soon.